All right, so we're going to be talking about momentum a little bit today. Here's a link to the PDF notes and a link to the video lessons. These things are all clickable in Blackboard under remote lecture materials. And let me first say what our basic momentum ideas are. First of all, momentum is a variable p, which is equal to an object's mass times its velocity. And all of these things, the momentum, the mass, and the velocity, are all properties of an object. So they all pertain to a single object. But one thing we like to do is combine objects, get a total momentum, which is the momentum of object 1 plus the momentum of object 2 plus dot, dot, dot. So we have this property of an object called momentum, and when I introduced energy, I said energy is like the currency of the universe because it keeps getting traded around. Well, momentum is another kind of currency of the universe. So how does momentum get changed? Well, for a single object, delta P is a quantity called impulse, I. Which is force times delta T. So if you exert a force for a period of time on an object, then you can change that object's momentum. And then so this is all about one object. When two objects interact, they interact by exerting forces on each other. Maybe they exert repellent forces on each other, or maybe they're attracted toward each other, or something like that. So we know F12 is equal to minus F21. That's the equation version of Newton's third law. And that means that the change in momentum 1 is minus the change in momentum 2. Which means that delta P1 plus delta P2 is equal to 0. In other words, delta P total is equal to 0. So and that is the idea of conservation of momentum. In physics, a conserved quantity isn't one that we're trying to maintain. A conserved quantity is one that stays constant all by itself. And in an interaction between two objects, that is, not interacting with the outside world, just interacting with each other, we have the idea of conservation of momentum. So let's do a quick momentum example. So let's say a 3 kilogram object is sliding across the floor with an initial speed of, let's go with 10 meters per second. And the friction coefficient is 0.5. So I want to know how long the slide is in both time and in distance. So the first thing I need to do is think about a schematic diagram of the situation. So we have this floor and an object with mass m, and at this intersection is a friction coefficient mu, and then there's the initial, and then the object is going to go forward, and eventually it'll get to here at a point where the final is equal to 0. So that's the situation. Now, in order to do an analysis, we need a force diagram. And every force diagram should include any distance forces. That is, a force caused by something not touching the object. Earth is not touching the object, not the entire planet, but the entire planet Earth is causing the force of gravity. So we have our force of gravity, which is 3 kilograms times 9.8, which is equal to 29.4 newtons. And then we have our normal force. Now you may know that the normal force is also going to be 29.4 newtons, but remember that you don't officially know that until after you've done your force analysis. And then we have our force of friction. So we do our force analysis in the y direction. We have force normal minus 29.4 is equal to 0. So now we officially know that force normal equals 29.4 newtons. For the sliding friction, force friction is the kinetic coefficient of friction times the normal force, which is 0.5 times 29.4, which is 14.7. And then we have the x direction, which is minus force friction is equal to mass times the acceleration x component. And that gives us 3 ways of analyzing the motion. So we have kinematics. Kinematics basically involves acceleration. So using kinematics, we would say a sub x is minus force friction over mass is minus 14.7 over 3, which is minus 4.9 meters per second squared. And yes, we could use that to answer the question. But let's use energy. So in an energy analysis, we can find the kinetic energy initial is 1/2 mv squared is 1/2 times 3 kilograms times 10 meters per second quantity squared is 150 joules. And then work is the change in kinetic energy. So we have 150 joules at the beginning. At the end, we have no kinetic energy. So that's minus 150 joules is equal to Fx delta x. That's kind of the definition of work. So our minus 150 joules is minus 14.7 newtons. That's my x component of the force. So this is the x component of the force. And then I have delta x here as part of my equation. So now I can take my 150 over 14.7 and just got a new phone. I'm still getting used to it. 150 over 14.7 is, I hate this calculator. I want my old one back. 10.2. Oh, 10.2 meters is equal to delta x. So we could have gotten that result from the kinematics, from the acceleration, and going back to our stuff from chapter 2, chapter 3. But we can also get it from energy analysis. And now we have a third method of analysis, momentum. And in a momentum analysis, our momentum initial is equal to mv initial, because momentum is calculated just by taking mass times velocity. So if I want the initial momentum, I use the initial velocity. And my initial my mass is constant. I don't need to say initial mass, it's just mass. So my mass is 3. My initial velocity is 10. So my initial momentum is 30. And my units of momentum are mass, kilograms, times velocity, meters per second. My P final is equal to 0 because my object comes to rest. And then my delta P is P final minus P initial is minus 30. And that is my force times delta T. So minus 30 is equal to my force, which is minus 14.7 times delta T. So then I can take 30 over 14.7 and get 2.04 seconds. Is equal to delta T. And we could have used the acceleration to find the amount of time instead of using the idea of momentum, but we'll find that momentum has some advantages that sometimes it just is easier to think about momentum than to go back to kinematics equations. So notice that energy links a force to distance. So force through a distance gives you the work, which is a change in energy. And momentum links a force to time. The change in momentum is the force times the amount of time. So that's a nice, simple, easy to break down momentum example that you can use to supplement what is available in the PDF notes and the video lesson.